Hello students. So till now we have studied many problems in quantum physics, like what kind of potential electron experiences or how electron behaves when it experiences a step potential, when its energy is less than the barrier, and what happens when the energy of the particle is more than the barrier. Then we saw that we took a barrier of finite width and which we call as rectangular potential barrier. And then we saw that when the energy of the particle is less than the barrier, even then there is a finite probability of the particle being reflected and transmitted quantum mechanically. The particle, if the energy of the particle is less than the barrier, classically we all know that it will not transmit. Why? Because the due to the less energy than the barrier, we have kinetic energy negative. Okay, so we'll try to see now. So we have done the step potential and the, so these were all the toy problems. Now in order to study real metals and solids, what kind of potential electron experiences and what physics do we get from there, and you will see that we really get a very deep insight when we study the interactions of electrons inside the metals or solids. So in order to study real metals and solids, so basically we are moving towards the real problem. Okay, and then we'll try to solve the Schrodinger equation and see what do we get. Solids, in order to study, okay, we will try to study, try to see how electron interacts with the positive ion codes. Okay, and what kind of potential it experiences, and then what kind of results do we get. Okay, now you all know that in a crystal we take a regular crystal. Okay, then we would be having positive ion codes. The distance between two ions we can take as a, the lattice parameter of the crystal, and then when the electron approaches, what kind of potential it will experience. As it comes close to the positive ion, the potential increases. You all know that potential varies as 1 over r. Yes, and then when it approaches center of the two positive ions, then it becomes 0. Again it increases, and this repeats. Correct? So what do we observe here? That the electron inside positive ion cores, okay, and the electron approaches. So what do we observe? That the electron experiences periodic potential in a crystal. Okay, yeah. So now when the electron experiences periodic potential, then how do we solve the Schrodinger equation? Okay, and what kind of wave functions we have to take. So there were physicists known as Kronig and Penny. They suggested a simplified model. They suggested simplified model consisting of infinite row of rectangular potential wells. Rectangular, rectangular potential wells separated by barriers of width b. Okay, this is an infinite row because we have a regular crystal. Infinite. Okay, by assuming this, so I can draw my problem as okay, so on, where this is v naught and this I take as b and this I take as a. Okay, this I can take as origin. So from left from the origin, this will be minus b and this will be plus a. Okay, now we can solve this problem because already we have seen that how the electron behaves when it sees a rectangular potential barrier. So this was simplified. Now the electron, we assume here that the electron has energy less than the V naught. Okay, so we will take E less than V naught. So our problem is very similar to the last problem which we have encountered. The very important difference here is that the potential which the electron experiences is periodic. So now, what kind of wave functions do we have when the potential was periodic was given by another physicist known as Bloch. He suggested that, so let us, so for a time being, I would little digress from the topic, okay, and then we'll try to see about what kind of wave functions do we have when the potential is periodic, and then we will again come back to our problem and solve the Schrodinger equation. Okay, so what we are going to do now, that what Bloch said. He suggested, Bloch suggested that for the periodic potential, so how do I write the periodic potential? V of x is equal to V of x plus a. Yes, or I can write SA. S is some integer. S is equal to 1 to A is my lattice parameter. If I have such kind of potential, then the wave function should have the form psi of kx is equal to ukx e to the power ikx, where k is the index to label the solution. Please don't confuse with the momenta. Label the solution. Okay. And ukx also is some other function also having the periodicity of the lattice. Ukx is equal to ukx plus a. Okay, this is my statement. This is known as Bloch's theorem. This was a statement which Bloch made. It also has the periodicity of the lattice. And these wave functions are known as Bloch wave functions. And this is known as Bloch functions, Bloch wave function. Okay. Now, before going further to solve the Kronig-Penny model, I would like to prove this. Okay, this is a very beautiful theorem. We'll try to see how Bloch suggested that the wave function should have this form if the potential is periodic. Okay, that is Vx is equal to Vx plus Sa. Okay, it repeats. Okay, that we have already seen that in our lattice such kind of potential is there. Now we'll try to prove this. Okay, so let us try to see. Okay, the proof of Bloch theorem. That was the statement of the Bloch theorem. Okay, now if psi x satisfies the Schrodinger equation so what is our Schrodinger equation? D2 psi x upon dx square plus 2m upon h cross square e minus vx psi of x is equal to 0. Okay, so my psi x, the wave function, satisfies the Schrodinger equation. Then I am saying that if such thing happens, then psi x plus a is also a solution of the Schrodinger equation with energy E. Is also a solution of the Schrodinger equation. This I am saying that it will be. We'll see how. Is also a solution of the Schrodinger equation of a particle with energy E. Okay, we'll see how. So if psi x plus a is a solution, then it should again satisfy the Schrodinger equation number 1. So if it satisfies psi x plus a, if I substitute here, it should satisfy. We'll see whether it does or not. E minus, so in this equation I replace everywhere x by x plus a. V x plus a psi x plus a is equal to 0. And because my potential is periodic, Vx plus a is equal to Vx. Okay, so what do we get? D2 psi x plus a upon dx square plus 2m upon h cross square e minus Vx psi x plus a is equal to 0. And this proves that psi x plus a is also a solution of the same equation with energy E. Fine. Now, I have shown you that psi x, if it is a solution of the Schrodinger equation, then psi x plus a is also a solution. This suggests me that if both are solution of the Schrodinger equation, this suggests that I can write psi x plus a is equal to c of psi x, constant times psi x. Okay, I can write this because both are solutions where c is a constant which may be complex, okay? Which may be complex. Now, let us try to see the crystal. Let us consider now, let us consider capital N identical lattice points. We are taking a regular crystal, lattice points on a ring. Okay, and this full ring is of length NA. Okay, so what do we have? We have like this: first, second, lattice points, and the lattice parameter is A. We take such n points, and after n it comes back, and total length of the ring is NA. Okay, then we can write psi of x plus A is equal to c of psi x. That already I have written, I have proved, because both are solutions. Okay, so I'm taking first, this is point x, this is point x plus A. So my wave function, it identifies this. Then psi x plus 2a will be c of psi x plus a. Okay, psi x plus 2a, it is connected to psi x plus a. Now psi x plus a, if I want to write this in terms of psi x, I will get c of psi x. Okay, from the previous equation. I can just note down the equation number. This is equation 3. Okay, so this is equal to c square psi x, equation 4. Fine. Now if I want to write psi x plus na in terms of psi x, what do I get? I will express this in terms of psi x plus n minus 1 into a. Yes, I will get one constant, and going back, if I write in terms of psi x, I will get c to the power n psi x. Okay, one can check. It's very straightforward. Equation number 5. Now, we know that the psi x value must be single valued, correct? So this should identify psi x is equal to psi x plus na. We know that psi x must be single valued. This is one of conditions the wave function should satisfy. Must be single valued. In such a case, when psi x and psi x plus na should be same, we get c to the power n is equal to 1. Clear? What does this show? It means c is one of the roots, one of the n roots of unity, and I can write that c is equal to e to the power I 2 pi s upon n. Okay, where s is the integer. Okay, therefore, now we have already calculated c. Therefore, we can write, we can write our wave function psi x is equal to some wave function ukx into e to the power I 2 pi s x upon na. This we can write, this satisfies equation 3. Which equation? 3. That psi x plus na is equal to c to the power n psi x. Because c already we have calculated. This is an exponential factor e to the power I 2 pi s upon n. Okay. This will satisfy, and okay, or this 2 pi s I upon na, I can, not I, sorry, 2 pi s upon na, I can take as k, 2 pi s upon na. In the beginning only I told you k is an index to label the solution, and you can see that s is also an integer. So and rest na, everything is constant, so k is also an index to label the solution. So I can write this as psi x is equal to ukx e to power I kx, provided ukx also satisfies the periodicity of the lattice ukx plus a. I hope you all can see that this is correct. I have proved that my c coefficient is the exponential factor. Yes. So when this is proved, we can write psi x as in this form, which is the Bloch wave function, provided ukx also satisfies the periodicity of the lattice. If you are not able to see this directly, I can show you. We can check that whether this satisfies or not. So what do? I will do that. I am saying that this form satisfies equation 3. Equation 3 is this one. Okay? Sorry, equation 3 is this one. Psi x plus a is equal to c of psi x. Let us try to check whether it satisfies or not. Okay? To check, I'll just name the equation. That was 3, 4, 5. This is equation 6. Okay? And this is equation 7. Now we have to check that whether equation 7 satisfies equation 3. To check that equation 7 satisfies equation 3. So I will start from the left hand side. In equation 3, the left hand side is psi x plus a. Okay, so in this equation I will take everywhere instead of x, x plus a. Okay, then what do I get? Psi of x plus a is equal to uk x plus a e to the power I 2 pi s x plus a upon na. Fine. Now uk x plus a e to the power exponential, this I can separate. How do I separate? E to the power I 2 pi s upon n separate. S into a upon na, a will cancel. I will get s upon n into e to the power I 2 pi s x upon na. Fine. Now what is this? You all know this is c. What is this? I can take this as back ukx, because I have already taken the condition that provided ukx satisfies the periodicity of the lattice. So I can write this as, this term I take here, 2 pi s upon n. This I take as ukx. I can write because it satisfies e to power I 2 pi sx upon na. What is this? This is C. What is this? This is my what I have taken. You can check here. In this equation, I have taken x is x plus a instead of x. Okay, and then finally I got ukx e to power I 2 pi sx upon na. That's what I got here. Yes, this is my psi of x. So I have proved that whatever the form of the wave function I have taken, it satisfies equation 3. It means the form which I have taken here in equation, just a sec, I'll just rub this by mistake, it should not. It should not get confusion. Okay, so I have shown you here that this form I am taking, it satisfies psi x plus a is equal to c of psi x. This proves that if the potential is periodic, then I can take my wave function to satisfy this form. Okay, so finally I showed that finally we got that what Bloch suggested was correct. If potential is periodic, okay, then my wave function can be written as ukx e to power ikx. This is the Bloch form where, but with this you have to write provided ukx satisfy the periodicity, and also what is k? K is I 2 pi s upon na. Correct? This is integers. Okay. Okay, this proves my Bloch theorem. Now what we will do, we will use this form of the wave function and we will try to solve our Kronig-Penny model, the real problem of solid when the electron experiences infinite row of periodic potentials. Then what results do we get? We'll try to see in the next lecture. Thank you.